I think we can start. So welcome to this week Autonomy Talks. This week is a pleasure to have Professor Morteza Lahijanian, who is an assistant professor in the Aerospace Engineering Science Department and the director of the Assured, Robust and Interactive Autonomous Systems Group at the University of Colorado Boulder. Something about him. He received a Bachelor of Science in Bioengineering from University of California, Berkeley, and then a Master's of Science in Mechanical Engineering at Boston University, where he also got his PhD in the field of systems and control theory with applications in robotics. He then moved to Rice University as a postdoctoral scholar, and he also joined the University of Oxford as a research scientist in the Department of Computer Science. His research interests span the areas of control theory, stochastic hybrid systems, formal methods, and game theory with application to robotics, in particular to motion planning, strategy synthesis, model checking, and human-robot interaction. In his lab, he develops novel theoretical foundations and computational frameworks to enable reliable and intelligent autonomy. And today he's going to talk about some of his recent developments, and we're very happy to hear what he's going to tell us. So go ahead, the stage is yours, Morteza.
Thank you for the introduction, and thank you for the invitation. I'm very happy to be here and excited to present some of our recent work. Just a little clarification about my background and the confusion maybe it has caused. I've gone from bioengineering to mechanical engineering to computer science and maybe back. And this was all for the love of robotics. I am a robot enthusiast. I would love to see robots move. And this path of desire to do things about robotics has taken me from bioengineering, where I wanted to do surgical robots, to formal methods and controls, and now working with stochastic systems. So today, I want to talk to you a little about a couple of projects that we started about a year and a half ago. And I think there are some interesting results, and I would like to share them with you. And as I said, I am totally excited by robots. And when they move, it totally gets me out of my skin, and I just want to jump out and, out of excitement, kind of shout. So that excitement comes with the addition that we live in an era that we are witnessing robots leaving their factory floors and entering our society. There are many examples around the world. This is an old video from Google car before it became Waymo. They released this video to show the benefits of having self-driving cars. So now in this video, they show a legally blind guy sitting behind the wheel and quote unquote driving to his favorite restaurant and pick up some food and maybe eat on the way back, something that he was not able to do because of lack of or weakness in eyesight. Robots are also becoming a matter of national pride. A few years ago, when President Obama was the president, in his visit in Japan, Japanese officials made sure they take him to visit Asimo and play balls with him, and Asimo get to show off some of its skills. So it has become even a matter of national interest and national pride. More on the daily basis, you see robots everywhere now. Now, this is Aloft, a robot that serves in, sorry, I think my computer is slowing down. It serves in hotels like in Palo Alto, California. They don't send housekeeping to your door anymore. It is the robot that delivers the goods to the customers or to the guests. So if you're staying at the hotel and you want an extra towel or a toothbrush, it will be Aloft that will bring you the requested item. And we are seeing a lot more robots coming in. Self-driving cars are getting everywhere, and obviously some of you are already affiliated with New Autonomy. It's one of the companies that are taking the lead in this area. And all in all, we are seeing a lot of autonomous systems entering our society. And that's just not in transportation. We see them in our air, like drones. We see them in space, like in, NASA Astronaut 2, which is in International Space Station and is performing some tedious tasks that humans, or we don't want astronauts to spend time on, like cleaning the rods of the International Space Station, which turns out to be a very important thing to do. And we have underwater robots these days that are very, it's a blooming field. And once in a while, we see these videos from like Boston Dynamics that show capabilities of robots doing things that only trained humans can do. Not a regular person or someone like me after a year of pandemic being out of shape, I can't do that. I can't pull that off anymore. But these robots can do it, and maybe some New Year celebration, coordinated dancing. All of this are a glimpse of hope for the future, but I want to claim that they may be a little misleading. What they suggest may be not a reality at this day and age that we are in currently. Many of these robots have shortcomings and they make mistakes, and those mistakes they become evident when we put them into test. Like in 2015, DARPA put up this challenge after they saw what happened in Fukushima in Japan when we had the tsunami, the nuclear plant was damaged, and then there was a leak of radioactive material, and we sent in humans to fix the problem. We put their lives in jeopardy. But DARPA came and said, okay, why do we send humans? If roboticists claim to be they're so good, they can build these autonomous systems, why don't we use robots to address such problems? So here's a test for you, roboticists. Here is a robot, have it drive a cart, get to the door, open the door, turn a valve, drill a hole into the wall, move the box, and just climb the stairs and declare victory. Or if you want, you can get more points by walking over uneven terrain or soft sand. And a lot of teams participated in this competition, and here's some of the results. Some of them are really hard to watch. Okay, that's where I wanted to stop. So the robot that we saw actually fell out of a car. It was a robot by, I believe, a group led by Ross Tedrick. So there are many issues that came up and many reasons for these robots to fail. Some of them may be because human intervention. They could have humans behind at every step of the way to program the robot what to do next time. And some of those humans were under pressure and made mistakes in their coding. And some of the other ones may be due to unmodeled dynamics, like walking on the soft sand. It's really hard to model those dynamics and then write control laws for them. And famously, Ross Tedrick, after the experience that this robot failed, he said, we went with more autonomy, as much autonomy as possible, because we wanted to rule out human mistakes. But we forgot to verify the system. And now doing formal verification and formal synthesis for our systems is a priority because we want to completely rule out errors. And that's what this talk is about. It's about ruling out errors and trying to replace all those details that we usually handle by hand, leave it to algorithms and then leave it to specifications, and they take care of it. Because if you have mistakes in this controlled environment, that's fine. It's not a problem because these are learning experiences. But if you actually employ some of these techniques and put on autonomous systems, bad things could happen in our society. And some prices are too high to pay, and there are usually these types of prices are embedded in the fact that we are using AI-enabled autonomous systems, where we use the AI, some sort of machine learning or trained neural net or some other functions that we use as black box in our designs, and we don't really know what to expect from the outcomes. So in my group, we are interested in safety and soundness in general. That's the central theme in my research in my group. We want to guarantee safety no matter what, and we want to have some sort of an intelligent way of reasoning about behaviors of system. And we want to do it algorithmically, and we use methods known as algorithmic approaches to correct by construction methods or control design. And this is a field that started in early 2000 when a bunch of control theorists were exposed to formal methods and started applying those in control theory, and then roboticists started applying those in more physical systems. So my research is at the intersection of control theory and formal methods. Well, I think everybody is familiar with control theory, and formal methods, I think, is fairly clear for those of you who are not clear what it is. It's essentially a rigorous mathematical rigorous method that reasons about system behaviors algorithmically from high-level specifications. And this is a subfield of computer science traditionally known as formal verification, and now it has made its way to robotics and control theory. And more recently, we are getting interested in machine learning techniques and incorporating these techniques into formal methods and control theory. So in my view, an autonomous system consists of these layers, and then these are purely engineering fields, but they are combined together, and that's what makes a system an autonomous system. It starts with electromechanical design, the design of the physics of the robot that is traditionally part of aerospace or mechanical engineering, electrical engineering field. And then you have control theory, where it enables you to design controllers for your system, very nicely stabilize it, make sure that everything moves smoothly. And then you have motion planning on top of that to enable the system to move in space with some subjective goals. And then on top of the top layer, it's decision making. That's what makes the robot actually autonomous. So if you want to have the Robonaut 2 to do a spacewalk and fix the exterior of the system of the space station, then it needs the capability of decision making, motion planning, and control theory, all of them combined. And everything here on top three layers, we work on in my group, except the bottom layer. We don't really work with design of physical systems. And we use it in context of formal methods, as I said. So correct by construction framework takes usually these things as input: formal specification, the environment, the knowledge that we have of the environment, and the dynamics of the system that we are working with. And the output of it is a control strategy for a system with formal guarantees that come out of it. And a bunch of things go inside this box that are slowly revealed. So if you want to design a system that is correct by construction, it always starts with the specification. What are your requirements for the system? What do you want your system to do? And in my world, the requirements are purely logical statements. And why do I use logical statements? Because first of all, if you want to use human language, it's very vague. You don't know what it really means. But logical statements are clear. There is no ambiguity in them. And then another advantage of logical statements is that you can always translate them to some mathematical objects like state machines. And unlike cost functions, which are traditional tools to use in controls domains, logical statements are a lot more expressive and strict, and do they put hard constraints on certain things and allow soft constraints on other things. So let's take this specification here as an example. Let's say I want my system to collect, or my robot to collect all dirty dishes and then wash them and eventually put them away, and do not put them away until they're dry. I can easily translate this to, let's say, temporal logic specification, where I can combine temporal operators like next, eventually, globally, with Boolean operators like and, negation, or. So this becomes collect and next wash and eventually put away and not put away until dry. And as I said, a benefit of having these types of specifications is that we can have algorithmic approach to construction of state machines or mathematical objects that fully capture what we want to do. So here I have a finite deterministic automaton, a DFA, which captures every way that my specification can be achieved. We start from initial state and ends in an acceptance state, which shown here as a double-edged circle. So if I start from initial state and I find a path to an acceptance state, that means that I have satisfied my specification. Let's take this as an example. Collect, wash, stay here as long as it's not dry, and then dry and put away. I'm here, I've done my task correctly. So in my world, the specification lives in a logical space. And of course, we have our physical space, which consists of the environment and the robot. So the automaton is what captures what we want to do. So one might think that, okay, if we want to have control synthesis, some sort of dictation, who should dictate what? It should be the logical space that should dictate this physical space what to do. But it's not fully true because the logical space doesn't know anything about the physical constraints of the system. For instance, take the bottom route here, the bottom path. So I collect, wash and dry and put away at the same time, and then you're done. The thing is, in a physical space, washing and drying and putting away all three at the same time may not be possible. Actually, I don't think if it's possible at all. So what we need is actually a two-way relationship between the physical space and the logical space. So if we break the physical space into environment and the dynamical system that we have, then we have the interaction between these three layers of dynamics, environment, and the logical space. And we need this back and forth communication between them. And a traditional way of breaking these apart is that we put the environment and the dynamics together and we construct some model of them to combine that we capture all the way they interact with each other. We call that a finite abstraction. In construction of this finite abstraction, we need to guarantee that all those behaviors are captured correctly. If we have those guarantees, then we can interact the logical space with the finite abstraction and perform things correctly. So going back to this framework, we can construct an automaton from our specification. We can combine the environment and dynamical system and construct an abstraction, and traditionally some sort of a Kripke structure, some transition system, some discrete structure. And we compose these two to construct something known as product automaton. This is just another discrete structure that we construct. And we do an optimal search, whatever domain that we are in, depending on the domain we are in, it could be, for instance, Dijkstra search, shortest path search. And that can map into a control strategy and a formal guarantees. And as I said, this has been studied since early 2000s in control theory and has extended itself to robotics. And there are many, many papers in this field and many examples of what this actually, how this works. And there's an interesting review paper that we co-authored a couple of years ago on this matter. And now people started looking at different variations of things that could happen. What if my environment is dynamic? What if my environment is changing? It's not static. Then what do I do? Then your abstraction, rather than a transition system, becomes a two-player game. You're playing against another agent in the environment that keeps changing components in the environment. And then the product becomes a two-player reachability game, and therefore you need to construct a winning strategy for the system, which means that under all possible actions of your adversary, you can win the game. That leads to studies like this, human-robot interaction. If I have a manipulator and I have objects in my environment, and I have a specification, let's say I want to build an arch, then if I know all possible ways that the human can manipulate objects and all possible ways that my robot can manipulate the objects, I can construct a game abstraction that captures everything. And therefore, I can construct a winning strategy that guarantees the completion of the task, no matter what the human does. So here, the task is build an arch with the white columns being the white boxes being the columns, and the black one being on top. Here, human comes to help by making a mistake of putting black box as one of the columns. And here, the human comes and being a little playful, moves away the box from the robot, but the robot puts it back in and finally puts on the black box to finish the task. So because we constructed this winning strategy for the system, we know that under all possible motions of the human, we can guarantee completion of the task. Or similarly here, the task of the robot is to construct a diagonal line with the black box being in the middle. And you can see that here, again, the human is going to be a little playful. And before the robot can place the black box in the middle, the human comes and says, oh, no, I want this diagonal. But the robot is able to react to the changes that human has made and finish the task quickly. Other things that could change in our domain is like we can have on-model changes in our environment. Then what do we do? If we can't know all possible ways that the environment can change, how can we overcome the complexity of synthesis problem? In that case, in our work, we split the specification into two types of constraints: safety constraints and liveness constraints. And we say that for safety constraints, we do not want to violate safety at all. We do not allow it. But we do allow violations to liveness constraint. And in that case, if things change in the environment and you need to react to them by violating your liveness, it's okay, you can do that. We just want to satisfy liveness as best as possible. And then we can construct systems like this that combine sampling-based techniques with automata reasoning to, for instance, the task of the robot here is either to go to P0 and then P4, or P1 and then P3. And the robot doesn't know that doors are closed initially. So it goes to every possible maneuver to visit those regions, but the doors are closed, and it decides to only partially satisfy the specification by going to P4. And that is actually chosen because it was the preference of the human by providing a little bit of information. And we can extend that to something even more complex, where the map is completely unknown, and we only know the initial state and the goal state that you want to get to. And we want to make sure that our system remains safe and gets to goal possibly as best as possible, but remaining safe is the priority goal. And here we can again combine sampling-based technique with chance constraint and local map constructions. And this is actually inspired by DARPA's subterranean challenge that was introduced 1.5 years ago. And here we have a quadcopter that, if the video works correctly, you can see that it places itself, it keeps motion planning, it's constructing the map here on top. And you can see that it's constructing a map, and it has layers of planners that allows it to quickly plan to the goal and build a funnel around its nominal path to guarantee chance constraint safety requirement. For some reason, the video is a little choppy, so I'm going to move on to the next thing. So another variation is, what if our system is stochastic? System being stochastic, that results in our abstraction being an MDP. And that's essentially what my PhD thesis was all about, how to construct an MDP from stochastic systems. I'm not going to get into details of them. It's just, we have a couple of examples. We have a robot in a warehouse where the specifications are pick up objects and then from the shelves here, phi 1, phi 2, phi 3, and dropped it off in P9. We can construct strategies for the robot. The abstraction takes a long time, but as soon as you have the abstraction, you can quickly compute different strategies for different specifications. These are all in seconds and with high probability of success that beforehand are all given. But what I specifically want to focus today is the problem that not only we have stochastic dynamics, but we also have partial knowledge of our dynamics. Then what do we do? What is the right way of formalizing this problem and finding control strategies with formal guarantees? So let's look at this problem a little more mathematically. So I'm given a partially known stochastic system. So x of k plus 1 is equal to f of x of k and u of k plus g of x of k, u of k, and w, where f are my known portion of dynamics and g is my unmodeled or unknown dynamics. And w is just a random variable. It could be noise. So you can think of that, for instance, I have a drone flying somewhere and there are drifts or there are weights attached to my drone. Let's say it's an Amazon drone and it's supposed to move boxes from one location to another or deliver boxes. By putting boxes on our drone, we introduce unmodeled dynamics, the swings that you might experience. Or another way of thinking about it is that f is more like linearized portion of my dynamics, and I design control laws based on my f. So I have a bunch of control laws, a finite number of them, but I also have high order nonlinear terms that I did not model, or they are in Simulink model and I don't have access to their closed loop dynamical model, and which is necessary for formal synthesis. So these unmodeled dynamics are a realistic way of modeling our systems along with the known dynamics. And sometimes I have fully unknown dynamics and everything in F is 0. So I have no knowledge of the dynamics at all. So if I'm given this system and noise, and in this case, I assume the noise is not necessarily Gaussian, it's more generally sub-Gaussian. Sub-Gaussian subsumes Gaussian noise. It's just as long as the tails decay as fast as Gaussian, it is a sub-Gaussian noise. So bounded support Gaussian distribution is sub-Gaussian noise. So given this dynamics and uncertainty, and a set of data. So if I don't have G, I want a data on input output of my system. I have X as my state, apply controller U, and give me the output of the system, xk plus 1. And I want M of these. I don't care, just an infinite number of these data points. And on top of everything, I have a specification temporal logic form. For instance, this one, it says with probability 0.95 or greater, always avoid unsafety and eventually reach destination 1 and eventually reach destination 2 in these two cases. So avoid unsafe and get to destination 1, destination 2. And I want that to be guaranteed to be more than 0.95 despite no knowledge of G. So the problem is to compute a control strategy for our system and a set of initial states from which I can guarantee that my specification will be satisfied. So this is our problem. And as you can see, there are lots of uncertainties here. I have the stochasticity due to noise. I have unmodeled dynamics, and I have a very complex specification. How do I go about this problem? So going to our beloved diagram here, I am going to show you the roadmap here. So from the input-output data, I'm going to regress a learning model for my G. And I am going to quantify the error of my regression. And I'm going to pass this information along with the known portion of my dynamics and the environment and construct an abstraction that is in the form of an MDP, but this is an uncertain MDP. It's called interval MDP, where the transition probabilities are not single valued, but rather they're interval valued. And then I'm going to construct the product automaton. And then because of all the uncertainties I have introduced here, I'm going to have to construct a robust optimal policy. And that's going to give me my control strategy. And I'm going to talk about the formal guarantees that come out of it. All right, so let's talk about the regression first. What type of regression do I do in this problem? But the first thing we tried was actually Gaussian process regression. The Gaussian process regression essentially requires a prior mean and a covariance function and a data set. And it uses joint Gaussian assumption with Bayesian conditioning to learn the posterior of my function. So if I rearrange my dynamics So in this case, G becomes x of k plus 1 minus f minus noise. Then I can actually see that I have G expressed in all the known terms. So if I have data on the output and the input and I know my noise distribution, then I can say that my data is an observation of my G with some noise. And here noise is obviously with a negative sign. So if I can rearrange my data so I can get observations of my G function, therefore I can regress a model, a Gaussian process model on my G, on my unknown dynamics. If I do that, then I can construct a mean function G hat and covariance sigma on how far away my my actual system may be from the mean. And that covariance tells me a distribution of uncertainties that I have. But the problem with Gaussian regression is that the assumption that G, sorry, my computer is going through some issues. Okay, it's back. Okay, sorry. The problem is GP regression assumes that G is necessarily a sample from Gaussian process. The issue is my W, my noise term, is not really a Gaussian process. It is a sub-Gaussian process. So it means my G cannot be regressed correctly using GP regression. And if I do that, my uncertainty that I've computed here is not true. Those uncertainties are fake, in fact, because I'm not satisfying the assumption. But the good news is a group of smart people from Cambridge and then TU Munich and now a bunch of group from a technical university in India, they realized that if you reason in RKHS domain in reproducing kernel Hilbert space, then with the assumption that your RKHS norm of G is bounded, then you can actually say something intelligent about the uncertainty or the error that you have as a result of regressing GP without satisfying the assumption of GP. And in that space, then if I have unknown, then I can say that my unknown function lies in the span of the prior covariance function or that kernel that I choose. And that really relates closely to the Lipschitz continuity constant of my system. And if I can characterize the Lipschitz continuity or find an upper bound of it, then I know that I can bound my error in GP regression using, so the error in my GP regression using this expression. So I have a probability that the distance between my actual function and what I learn as the mean of my GP is bounded by some epsilon. I can quantify this probability. And I'm simplifying here. Epsilon is very, it has a very ugly expression. It depends on the RKHS norm of G and also depends on something called information gain term that are hard to compute, but we have formalized them in our work how to compute the upper bounds for those terms. Therefore, we are able to find an upper bound for this probability. So I can compute the error of my regression. So I can regress my unknown function. I can infer it from data. I can precisely, well, not precisely, but loosely bound the error. I can find an upper bound for the error. So if now I have my G hat and the error, let's construct our abstraction. So from an initial state X, I know that the posterior of my system is going to be a Gaussian distribution. And I know exactly where I'm going to be in a Gaussian distribution within some range. The problem is this is only true for one-step evolution. If I wanted to do it more than one-step evolution, the posterior of two steps is not quite a Gaussian anymore, and I can't quantify the error. So I'm going to use the old trick in formal methods. And now what I'm going to do is I'm going to construct an abstraction based on a space discretization. I'm going to discretize my space, let's say using a grid. I can use anything else, like say hypertriangles or polygons or polytopes or whatever you want. And I'm going to construct a discrete model where each discrete state is going to be associated with a cell of my discretization in a continuous space. Then I need to find relationship between these discrete states, which means I need to find the relationship between pairs of these regions. So let's say Q and Q prime. Because my system is stochastic, obviously I'm going to have a transition probability between Q and Q prime under a controller U. But more precisely, I am here bundling bunch of continuous states into one discrete region, which means each continuous state can give rise to a different transition probability to Q prime. So maybe a transition probability from this state to Q prime would be different from transition probability from this state to Q prime. That's despite my regression error. This is purely due to discretization that I'm doing. So I'm introducing an error by discretizing my space. And that discretization will not allow me to have a single value transition probability, but rather I'm going to have a range of transition probability. On top of that, I also have the regression error that I need to account for. So I need to somehow find the range that my transition probability belongs to. I need to find an upper bound for it and a lower bound for it. So there are three sources of uncertainty that I have. One is the stochasticity of my system. That's natural to it. Another one is the regression error that I'm introducing by just collecting data and regressing the unknown function. And third one is by space discretization. I am introducing a level of error by doing space discretization. Okay, so now I need to, the best I can do is find some sort of a bound on this transition probability. Here I'm going to get a lot of mathematical, but I try to give as much intuition as possible to hammer home some of these points. Let's write the transition probability in terms of regression error that we have. So let's say my transition probability from Q to Q prime under controller U, I can write it as condition to the regression error that I have. So it will be a transition probability from Q to Q prime under U conditioned on the fact that the distance between my regression error is bounded by epsilon times the probability that it's bounded by epsilon plus the complement of it. The probability from Q to Q prime condition that my regression error is bigger than epsilon times the probability that the regression error is bigger than epsilon. So this is just very general rule of probabilities, conditional probabilities, and I've done nothing fancy here. But now I can actually start looking at each individual terms and see which ones I don't know and which ones I know. I know for a fact that RKHS bound gives me this probability, and consequently, this is 1 minus that, so I have this probability as well. So all I need to do is look at this term and this term. So let's look at that term. This says transition probability from Q to Q prime, given that I have a regression error of epsilon. I want to bound this. The way I'm going to bound this probability is that I'm going to expand my Q prime by epsilon, because I know that my error is bounded by epsilon. And another term, let's say some constant eta. So I'm going to expand this set. And I'm going to find the posterior of my Q region using my known function and regress function. I call it posterior image of Q. If these two sets, if yellow or orange and blue, they do intersect, it means that the probability that my noise value is within eta is bounding this term. It's because I have expanded my Q prime by the error term epsilon, and in this case by some noise bound eta. And I found the path posterior of my Q, posterior image of my Q, and by intersecting them, I know that my noise is definitely less than or equal to eta. So that probability is easily computable, and that upper bounds this term. And for this term, I'm going to just say that in the worst case, that probability is going to be 1. So it's upper bounded by 1. And for the rest of the terms, I know exactly their values. I can compute their values. Therefore, I can find the upper bound of my transition probability. If Q prime, the expanded Q prime, and the image of Q, they intersect, their intersection is non-empty, then I get this term times this term plus this term over here. If they do not intersect, then that becomes 0. It means that my noise has nothing to do with it, and I only get the error due to my regression. That's it. I'm done with the upper bound. I can do a similar thing for my lower bound. In this case, I'm going to shrink Q prime with respect to epsilon and eta, and look at the intersection with the complement of Q prime, and that is now lower bounded by this probability. And this term is lower bounded by 0, so I can compute my lower bound in general. So what I have done is essentially conformally, I have computed the upper bound and lower bound on my individual transition probabilities. So I'm going to construct a model that has states like MDP, transitions like MDP, and actions, but I have ranges of transition probabilities rather than single value transition probabilities. Okay, so taking a step back, I'm going to construct an automaton from my specification. Then I'm going to regress my unknown function using a GP and quantify the error, and then construct this abstraction in terms of an interval value MDP. And then I'm going to take the product of these two. Essentially, this product is all the ways my system can satisfy the specification, and I inherit the accepting state from my DFA, and I inherit actions and transition probabilities from my IMDP abstraction. Now the task is finding some sort of a strategy on these objects such that I can get to my accepting state. If I can get to the accepting state, then it means that I can satisfy my specification. But how do I compute this path or policy or goal or probability of getting to an accepting state? Because I have ranges of transition probabilities now. Well, there are several interpretations of this model. One interpretation that I like and I always use in my work is that it's a two-player stochastic game. What does it mean? It means that there is a player that picks actions, and there is another player that picks what transition probabilities need to be chosen for taking a transition. So let's look at this state Q0, Q1 is Z0. Under action A1, you have this transition probability range to go to this state, and under the same action, you have this transition range to go to this state. So from Q1 Z0, if I choose action A1, then I have an adversary, which is essentially all those uncertainties that I mentioned, the error in the transition, the error in discretization, error in regression, and the stochasticity. All of those uncertainties. Once I pick an action, they are going to determine what the transition probability is going to be. And that transition probability need to respect the range that they belong to, and also they need to add up to 1. It has to be a true transition probability. So I, as one player, choose actions because that's in my control. And then the uncertainty, all the errors I've introduced, that's going to pick what transition probability I'm going to use to transition to the next state. With this interpretation, then I am playing against uncertainty. And since I am looking for a robust optimal policy, I'm going to think that uncertainty is playing against me. It's going to want to work to have the worst possibilities for me. It's going to choose the worst transition probability distribution for me. So if my objective is to maximize probability of achieving or arriving to acceptance state, the objective of the adversary is going to be minimizing the probability of getting to acceptance state. So I can write it this way. Maximizing over actions, those are my choices, minimizing over transition probability distributions of the probability of eventually getting to an accepting state. This will give me an optimal, robust policy. So how do I compute that? I can formulate it. How do I compute it? Well, in previous work, we showed that you can actually use a method similar to value iteration. It's called interval value iteration. The complexity is polynomial. It's very nice. You can actually use this method to compute robust strategies for your system. So once we compute this robust strategy, then we can actually now pass down the strategy to our system, which will be an assignment of a controller to each discrete region. And what will happen to my guarantees? Well, my robust strategy is going to be robust against the discretization, regression, and stochastic uncertainties. And the probability of satisfying the specification from every continuous state is going to belong to the range of transition or a probability of success, with the lower bound and upper bound given as the lower bound being what I computed for the policies, and the upper bounded when, oh, this is a typo, this should be max. When the adversary is playing with me, the adversary is actually helping me to maximize probability of getting to an accepting state or satisfying the specification. So having these two actually allows me to quantify the distance to the optimal probability. So because of all these errors, obviously I cannot compute the optimal adversary or optimal strategy to satisfy the specification. But I can quantify how far I am from that optimal probability, and that is upper bounded by the distance between the upper bound and lower bound. And the way, if I find some places that this value is really high, I can actually refine my error. So remember, some of the errors are due to discretization. So I can refine my discretization to smaller and smaller regions to reduce the error of discretization. And if the error is due to regression, I can add more data to those regions to increase my confidence and bring these two bounds closer to each other to reduce my distance to optimal probability. So this way of quantifying my error will really help me to identify regions where I need to do refinement, both in terms of discretization and regression. Okay, so does it really work? Well, we are still at the beginning of this research, but yes, the initial results are quite promising. We've done experiments, well, I shouldn't call them experiments. We've done simulations with linear systems and non-linear systems. So let's say I have a linear switched system, which everything is unknown. I have 3 modes, A1, A2, A3, and all of them are unknown. The only thing I know is some noise distribution for how my system is uncertain. So 3 modes, we collected 200 data points randomly, didn't think about anything. And the environment consists of obstacles and destinations. The specification was globally not obstacle and eventually destination with probability point greater than or equal to 0.95. So we did the regression, abstraction, and passed it to the robust control policy synthesis. And here is the result we obtained. The purples are probability of satisfaction of 0. You do not satisfy the specification from these regions. And that makes sense because those are actually obstacles. If you start from those regions, you're dead. So you do not satisfy the specification. And then we have these wide regions. And those are the regions we can guarantee that under the policy or under control strategy we have computed, you will definitely satisfy the specification. In other words, the probability of satisfaction of this property is above 95% from these regions. So from every wide region, we have a control policy that will guide the system to satisfy the specification. And then interestingly, we have these regions, these light purple regions that we don't know if we have, if we can satisfy the specification or not. And that's because the lower bound of satisfaction is below 95%. And the upper bound that we computed is above 95%. So under certain adversary choices or uncertainty values, you may satisfy the specification, and under some other ones, you may not satisfy the specification. So that makes a very interesting case. That's actually where we can quantify, we can look at distance to optimality. And if we find that distance to optimality is large, then we can do refinement, both in terms of data and in terms of discretization. All right, more cases. Oh, here we just did a study with respect to eta. How does the value of eta, the bound on the probability on the noise, changes things? And this experiment shows that as you increase the value of eta to be closer to your variance, what you get is a much cleaner and responses. So the larger the eta choices are, the better and better verification and synthesis results you will get. And it is obvious, and essentially that's what it's saying, that is that your expansion of Q prime is going to be larger, and therefore you allow for more intersection between the posterior of Q and expansion of Q prime. Finally, we also did some experiments with nonlinear systems. So we have a known portion X and nonlinear portion G, where this is essentially modeling a first order car. So we have sine and cosine in our nonlinearity term, and we look at the specification of eventually going to the destination. And here, the white regions, you can see that the probability of satisfaction is greater than 95%, so we can guarantee those. And here are some trajectories. The initial state is the points that are not marked, and the tail or the finish of the trajectory is the star. You can see that from all the points we have indicated that the probability or the satisfaction is guaranteed, the trajectories actually arrive to destination, and they do not leave the safe set. Whereas here, the purple ones, we simulated the trajectory and it leaves the safe set. So there is no probability of that we cannot guarantee anything here. We actually can guarantee that you will not satisfy the specification. And again, we have some purple areas here. And looking at the distance to optimality, we realize that these wide regions are essentially optimal. The distance to optimality is 0. Interestingly, this part where we declare that we do not satisfy the specification, the distance to optimality is large. So that means that we can maybe do more data analysis here and maybe turn some of these to white regions. All right, finally, more complex specification. Again, 200 data points. We can see that here we have two destination visits, D1 and then D2, and avoid obstacles. And by doing this, we find this white region, and we have simulated trajectories. They all start good and end well. They all satisfy the specification. We also look at some maybe regions and simulate the trajectory. And you see that, for instance, here, when you simulate trajectory, you end up in an obstacle. But here, when you start from this, this initial state, your trajectory actually satisfies the specification. So this shows that we can do a lot more in this area. And this is some sort of future work that we are doing. We are saying that, okay, we have some offline data and we have some offline strategy we computed. Can we deploy our system using that strategy without, by putting a hard constraint on safety and say, okay, do not violate safety, but collect data. So as you're executing, you're collecting data and you can improve on your regression. So online, you can update your regression and therefore reduce your uncertainty. And as a result, you can see that you can improve, but it will be very expensive computation to perform online. To do it online is very expensive. But what you can do is you can use local updates to your GP. You can use local GPs. And that's something that we are looking into right now. And it's very promising, actually. So here, we reduced the data points from 200 to 50. So everywhere was purple, nothing light purple. So nothing was certain. We could not guarantee anything. But when we initialized the system here, we saw that it does not violate safety, and it keeps moving around here, collecting data, We did not design that. It just happened. The system actually moved around until it collected enough data to be able to make the leap and satisfy the specification. From this initial state, we did not have to collect a lot of data. Every time we deployed the system with the offline policy, it satisfied the specification. This is an interesting case where the system does not violate the specification, and it keeps moving around to gather more data and reduce its uncertainty. And it does, but it's not enough to make a leap and go satisfy the specification. So there is some work to be done here. So we terminated trajectory after 1,000 time steps. Did not violate the specification, but it did not satisfy it either. So some areas for research that is very interesting. Okay, so I think I'm out of time, so I'm gonna stop. But one more topic that we've been looking at is writing these specifications may be very difficult, and we want to actually learn these specifications rather than writing them from data, from demonstrations, from previous experiences. And that's something that we are now actively doing. So I'm just gonna conclude now by saying that today's autonomous systems are becoming more and more capable, and that's as a result of the advancement that we have in technology, especially machine learning. And a lot of effort has been done in making the system smarter, but not so much safer. In terms of safety, we are still lacking. And I believe, I'm maybe biased, but it's a strong belief that formal methods, formal reasoning can help us a lot in this area of providing safety for our systems. But with formal methods, always we have the traditional problem of computational complexity. But if we could employ some of the machine learning techniques that are so powerful now within the framework of formal methods, we may overcome some of these problems and solve some interesting problems that we haven't really looked at. So there are other groups who are looking into these problems or integration of machine learning with formal reasoning. My group is not the only one, but this is quite a young field, and there are a lot of people trying to get into it now. All right, so last but not least, I would like to, this research obviously is not possible without a strong group of people behind me who actually do the work. I just do the talking, they do the work. I don't do really anything other than just thinking about the problem and telling them what to do. Really nice people, my students. The people in yellow or orange, they are the students who worked on this project, or the projects I spoke about, and my collaborators here at CU Boulder and TU Delft and Cambridge, and I'm very grateful with all the brainstormings I've been doing with them. On that note, I would like to open the floor for questions, and thank you for listening to me.
Thank you, Morteza, for the talk. Are there questions from the audience?
Yeah, thank you, Reza. I have a question. Yeah, it was very interesting, the way that you deal with the chance constraints and, like setting these guarantees on, some probabilities of things happening. But I was curious, what is the semantics of that kind of statement, especially if you have infinite time horizon kind of trajectories?
Right. So in which context? In terms of like unknown dynamics?
Right. So for example, what you have is, okay, so now you have a system, right, that has to visit a number of locations, and maybe you have some liveness property that says that you eventually have to reach, both of these locations, right? So essentially, right. You will get to some infinite time trajectory that right. alternates between the two, right? Now, when you say that with probability 0.95, you will not get in trouble, things like that. So now this is a statement that has to be interpreted over the infinite time horizon. In what sense yes. is that true, right? So
okay, yes. So I can give you a traditional formal methods answer, and then I can expand on it to what happens to actual unknown systems. So the traditional formal methods answer to it is that with MDP abstractions, for instance, we can look for end components or maximal end components in our MDP, which defines a subset of my MDP where I have probability 1 of visiting all the states in that component and never leaving that component. Mm-hmm. So when I say I have probability of 95% of satisfying the specification in infinite horizon interpretation, it means that I have a tail or reachability probability of 95% to this end component. And then once I'm in this end component, I remain in that end component forever with probability 1. Mm.
Okay, so essentially but at that point, essentially the stochastic component really doesn't play a role anymore.
It may
it's
play
a role because you have probability 1.
It may play in branching into other states, but from those states, I can come back to my initial states, let's say. Mm-hmm. So the probability branching could play a role, but as long as I am contained within a subset of my MDP, I can guarantee staying in that subset forever. But it would be much harder to do when you have uncertainty in your transition probabilities, mm-hmm. because your end components change according to the choice of your probability distribution, the choice of the adversary. And that shows, so MDPs, computation of end components of MDPs is polynomial. It's very well known how to do. Computation of end components for IMDPs turns out to be much harder. It could be, you could have exponential number of them. So your chances of actually terminating in finite time in terms of computation is really low. So what I do in this case, I look at interpretation of time, interpretation of LTL over finite horizons. So I look at LTLF. Mm-hmm. Linear temporal logics interpreted over finite traces.
Okay, but then if you So when you move to the receding horizon kind of formulation, then how do you do the budgeting of your chance constraints, right? So let's say that you took some risk for some time interval. Then what does it mean for your chance constraint moving forward?
So I believe you are talking about this latest results that we have here, more like we are guaranteeing safety not to be violated with 95%. So what is happening here is that the system is picking actions. So because the system is online, it does not suffer from space discretization error because it knows its current state perfectly. And it's collecting data as it goes along. So it increases its, or reduces its uncertainty in regression.
Yeah.
So it picks the immediate action that does not violate safety. So for us to incentivize the system to make progress, we also look at an objective of minimizing distance to satisfaction based on the graph distance to an accepting state. So first objective is not to violate safety. The second objective is to minimize distance to an accepting state. So when possible, it remains safe. When possible, it makes that leap over here to go to satisfy the specification. Whereas here, it has, even though it has some incentive to go to satisfy the specification, but the safety probability is so violated if it goes that direction that it does not do it.
Okay. Thank you. Yeah, I don't want to hog all the question time, so this, somebody else.
Yeah, but this is very interesting because these are results that we are just obtaining, and we find there is a lot of research to be done here to grasp a better understanding what's going on.
Yeah, I agree. Yeah, that's very interesting. Yeah, thank you, Morteza.
Of course.
Do we have
yes.
Anybody else?
Yeah. Hey. Can you hear me well?
Yes.
Okay. So I wanted to understand a bit better the semantics of the noise, and I realized that maybe I didn't follow the construction very well. But if I understand correctly, you treat noise as an adversary, right? So that you think about what's the worst that could happen. So I was thinking, for example, so let me give you an example. Suppose that you are you don't have any control authority, so you're just a Brownian motion. So so there is noise acting on you, and you're in a box. And now take the objective of maybe decide your destination. And what I want to say is that eventually you bounce around the box and you get to the destination. So that would be the result for that case. However, if I interpret the noise adversarially, then I will think, oh, this noise actually is doing its best to keep me away from the destination. Do I understand correctly?
Yes. Okay. So I think I understand your question, and I think I understand it correctly. If I have no choice in control, so if I have no you, and everything the only thing that I have that drives the system is the noise, then my analysis of the system essentially becomes a one-player game where I'm trying to find the correct slide here. So I do not get to choose the action anymore. It is the adversary or the uncertainty or / noise that gets to pick the worst probability for me. And therefore, the problem is not a synthesis anymore, it's a verification. And in verification, you just analyze what is the worst behavior of a system in terms of violation of your specification. And that's the correct interpretation. In formal methods, we try to be as pessimistic as possible. What is the worst thing that could happen to you? What can noise do to you in the long run? and that's what it will do. If you cannot satisfy the specification, you cannot.
Okay, so it's fair to say that it's very conservative, right? I don't know if
Yes, it's very. I'm not sure if it's unnecessary, but it is conservative in a sense that you have no control over the system, and noise is driving your system. And in the worst case, your system cannot satisfy the specification. Therefore, you can't satisfy your specification fully. I cannot guarantee that you will satisfy your specification. That's a better way of saying it.
Okay, so maybe that's maybe something to work on, because if I think, for example, to the Roomba, which I love, I also share the same excitement about robots, and I love the Roomba. It's like perfection in design, especially the one without the camera at the beginning. And so that's based. So maybe you can have a specification that says eventually everywhere, right, where you can fit, and it works because you bump randomly, essentially, right? So eventually you get everywhere, not very efficiently, but eventually. However, that is not captured by this analysis type, right? Because you basically you only consider the bad kind of noise, right? Sometimes it's also like a good kind of noise.
Well, then why wouldn't this capture it? Because if you're bumping to the wall is not a violation of your specification, and you're letting your system run for infinite number of time steps, then this model should capture visiting all the states, unless there is some end components, as you were just discussing with Emilio, sorry. If there are some end components that you can get stuck, if the noise can push you and stay there forever and you get stuck there, then yes, there may be a corner in the room that you may not get out of with no matter how many bumps you have on the walls. But I don't know, I would characterize it as unnecessarily conservative. It's conservative in terms of verification, but and providing guarantees. But if you want, to be correct, and if there is like 5% chance that you will get stuck somewhere, then this will tell you that there is a 5% chance you will get stuck there.
I mean, this will tell me, well, now it really depends on the geometry, right? So, but we don't have time to formalize the geometry, right? But this will tell you that if, for example, you can introduce a bias, to just let me bounce a little more to the left, a little bit more to the right, and at that point you might be able to get the Roomba trapped, right? Instead, like,
okay, so. Yeah. Let me put it more correctly. If we put aside the error due to space discretization, because that's an artificial error we're introducing. If we put that aside and say the only error and uncertainty that we have is due to noise, then the model should capture all the way your system can evolve over time. So if you say eventually everywhere, and that's possible, the model will capture it, and this interpretation will work. But if we go ahead.
Yes, I think this is really the problem of the field, right? Because at some point you want to put probabilities together with formal analysis, where you have if there exists a realization, and instead probability you don't care if things are measured zero. Right? I think that's the main problem here. That there is a realization of noise that will keep me trapped forever, but it has it's probably zero, tending to zero very fast, right?
So that's essentially the discussion we had right before this question. If the door of the room is closed and Roomba is circulating there, bumping to the walls and going everywhere, then this is essentially one gigantic bottomly strongly connected MDP or Markov chain. the probability of visiting every state is 1 in the long run. That's captured in this framework.
I'm not sure about that because if I understand that with that model, we'll get everywhere, right? So we eventually get everywhere. But then you're saying here, well, but I can be an adversary in choosing the noise, right? So for example, if it's a Brownian motion, I will choose a positive, +1, right? So you say, this is not, I cannot verify that because there could be that choice on noise that will keep me trapped.
Okay, so if we have no error due to regression nor discretization, we will not have these ranges of transition probabilities. And if we do not have the ranges of transition probabilities, then the choice of the adversary is singular. You will have a Markov chain. And in that Markov chain, then there is no choice for adversary, and therefore we should get the true model. But we have ranges of transition probabilities here due to error in regression and error in discretization. And because of those errors, yes, you're right. The adversary has a choice that would make maybe non-existent in real world, but because we have introduced it in our abstraction, we capture that. And that is a very conservative lower bound that we compute, and that is, for instance, the probability would be 0, probability of visiting all the regions.
Okay, I'm very curious actually. Maybe I should go and read the paper. But thanks very much for the talk.
Of course.
Hi, is there time for more questions?
Yeah,
I'm
maybe
here.
a short one. Yeah, go ahead.
Okay, then I'll ask the short one. Yeah, so what was the motivation for modeling noise as a sub-Gaussian? Was it like because of the mathematical tractability that you talked about, or was there like a control theory or a practical consideration?
Well, we started, to be honest with you, we started with actual Gaussian distribution first, but it was restrictive. Like you could not model truncated normal distributions, for instance. And the math was also quite simple. If you have Gaussian distribution, then you can do GP regression, no need for quantification of these probability of errors, you're all set. But as soon as you have more realistic cases where this is sub-Gaussian, then the theory gets more interesting and also the system becomes more realistic.
Okay, so it's a practical consideration. And so you got lucky that there was actually some mathematical work done for sub-Gaussians.
So we were lucky to find those works, yes.
Right, yeah.
Because we were struggling with it.
Another quick question about like the coarse graining. Like, can you put like priors on the coarse graining, like give it a good ontology or something like that, and like lower the error bounds or something?
So that was the motivation that we got to the online learning. So if you have an offline analysis, then you can definitely say, oh, these are the regions I need more data and more refinement. Therefore, let's go there, let's drive the system there while maintaining safety. We are trying to go in that direction, but since we are very conservative in terms of safety, it's really hard to push the system in that direction of the space. So the question is, yes, the answer is we know which regions we need more data, but we can't push our system there because those areas are not safe enough.
No, but like the carving itself, like, so you had like a tessellation, a very uniform grid, right? So could we like choose the states in a smart way because we already know something about the
the discretization, yes.
The discretization,
yes. We have actually, not with unknown dynamics, but with known dynamics, with linear dynamics, we choose the discretization. It's a HACC 2019 paper. We show that the discretization should be done in such a way that when you make a transformation to the space where your covariance becomes diagonal matrix, then your computations become a lot faster, and you can take advantage of that type of discretization to overcome computational complexity. So yes, you can choose your discretization according to the dynamics that you have and the knowledge that you develop on, or the intuition you develop based on your system.
But
For
in the online learning sense, you don't even have to worry about that because you'll just uncover whatever structure you need to on the fly, right?
I think so. That's my intuition, but we haven't really done the work to be able to answer that question.
Cool. Thanks a lot for the talk.
Mm-hmm.
I have some quick question if there is time.
Sure.
So thanks, Morteza, for the interesting talk. So my first question is regarding this constructing interval MDP. We already know that this is very expensive compared to the standard one. So the question is, do you leverage any property of the dynamics like monotonicity or mixed monotonicity of the dynamic to reduce this complexity or not? This is the you don't need any property. And the second question, just as a shot, so if we translate this setting that you presented, but instead of this interval MDP, we use, for instance, barrier certificate. So we have some partially known model with this setting and this type of a specification. So we know that the barrier is discretization free, but is there any point here that has benefit compared to barrier certificate that you selected actually this type of construction for interval MDP?
Well, yes and no. So first of all, do we use any dynamics property to reduce complexity of construction IMDPs? I'm not sure if construction of the IMDPs is more complex than constructing an MDP. The thing with MDP abstraction is that you need to account for an error. You can use a work by Alessandro Abate, for instance, that you use a representative point and then computes the upper bound on the error, but it turns out to be so conservative that you cannot compute infinite horizon properties on it. Or realistically, that error explodes so quickly that you can't really get a practical.
Yeah, sure. But by conservatism, by complexity, yeah, I know the standard one doesn't handle infinite time horizon property for sure. But at that point, representative point, just we need to take the integral one time. But now you are computing lower one and upper one. You are doing the computation 2 times, right?
Well, so if you know the transition kernel, and you know some let's say gradient descent optimization, then you can compute these upper bounds and lower bounds really quickly. And I refer you to our paper in HSCC 2019 that I just mentioned, that you can see how these computations can be done really quickly. I'm not saying this is the most efficient way. What I'm saying is it can be efficient, and the benefits that you get for it is worth the extra computations.
Okay.
And the second question you had about barrier certificates, that's definitely another approach. I would say it's orthogonal to this approach, because you're looking for a certificate to guarantee these transition or uncertainties over finite horizon. And I think George Papas, Majid Zamani, and those folks are working on those methodologies. And we are also slowly looking into that.
But if the noise is multiplicative, noise multiplied by state, still we can provide the guarantee for infinite time horizon. If we yes. Go for the martingale property, not C martingale,
if you go,
right?
Yeah, finding that barrier function might be not so easy. I mean, people use SOS, but I'm not sure if that's the best way to do it. But anyway, you still need to have control affine dynamics. In this methodology, you don't need control affine dynamics. Again, pros and cons. There are orthogonal approaches, and I think both need to be explored. In this case, abstraction would really help us to identify where we need more data. In that case, you have these envelopes of safety, and you're good as long as you have the function.
Okay, thank you.
Mm-hmm.
Thank you, Morteza, and congrats for handling that many questions. I think you triggered a lot of attention, and to the audience, if you have deeper questions, I suggest you contact directly Morteza and set up a meeting. Thank you very much for
and thank you for the
your talk.
invitation again, and thank you for this opportunity to share my work with you. And the great questions, very insightful. Thanks very much.
Thank you. Good luck for your research, and to the others, see you all next week. Or actually on Wednesday, we have another Autonomy Talk on Wednesday. Bye-bye.
Thank you, Morteza. Thanks again. Bye.